Models exist to simplify reality. They allow us to describe, predict, and act upon systems that would otherwise be too complex to grasp. Every scientific advance depends on this reduction. But every reduction carries a cost. A model is never reality itself. It is an agreement about what can be ignored. Every model assumes limits. Limits of scale, of stability, of linearity, of context. These assumptions are not weaknesses, they are what make models functional. Within their domain, models can be extraordinarily precise. Outside it, they become misleading. Problems begin when limits are forgotten. When a model built for equilibrium is applied to systems driven by feedback. When linear reasoning is imposed on nonlinear dynamics. When optimization is pushed beyond the structure it was designed to describe. At that point, failure is not an accident, it is structural. Models do not fail because they are wrong, they fail because they are pushed beyond their domain. Precision does not degrade gradually. It collapses once critical thresholds are crossed. What looks like error is often the system signaling that the model no longer applies. Limits are not obstacles to knowledge, they define where knowledge is valid. Ignoring them does not extend understanding, it produces false confidence. And in complex systems, false confidence is not neutral. It accelerates instability, amplifies feedback, and turns slow degradation into sudden collapse. To study limits is not to abandon models, but to respect them. Because every system that ignores its limits eventually reveals them, not through theory, but through consequences. Constants appear in science as anchors. They give us fixed reference points in a changing world. Without constants, equations would drift, predictions would dissolve, and measurement would lose meaning. In that sense, constants function as stabilizers. They hold structure in place. But constants are often misunderstood. They are not universal truths in isolation, they are expressions of stability within a specific regime. A constant does not describe reality everywhere, it describes reality where structure remains coherent. Take pi. It defines the relationship between circumference and diameter, but only within Euclidean geometry. Change the geometry, and pi no longer behaves as expected. Its meaning depends on the space it inhabits. Consider Euler's number, E. It governs growth and decay in systems where accumulation is continuous and proportional. It appears in finance, population dynamics, thermodynamics. But it holds only as long as growth remains smooth and the system's feedback stay bounded. Even physical constants follow this logic. They stabilize equations under specific conditions of scale, energy, and interaction. They allow models to function, because the underlying structure is stable enough to support invariance. Constants are not independent of structure, they are signatures of it. When the structure changes, constants lose their power. Not because they are wrong, but because the system has crossed into a different regime. At that point, equations still exist, but their meaning degrades. Precision becomes local. Prediction becomes fragile. Constants work only while structure remains stable. Beyond that stability, they stop anchoring behavior. And when anchors fail, systems do not slowly drift. They reorganize, bifurcate, or collapse. Understanding constants, then, requires understanding the conditions that make them valid. Without that, constants become symbols of false certainty, precise numbers applied to unstable worlds. As systems approach their limits, something fundamental changes. Constants do not disappear, but they lose their explanatory power. The system no longer responds smoothly to variation. Instead, it begins to split. This is the point of bifurcation. A single trajectory becomes multiple possible outcomes. Small differences in conditions no longer converge toward the same behavior, they diverge. The system becomes sensitive to its own history. At this stage, constants still exist mathematically, but they stop governing behavior in a reliable way. The same inputs no longer produce the same outputs. Stability gives way to branching. Chaos emerges not as randomness, but as structure without predictability. The system follows deterministic rules, yet its future becomes practically unknowable. This is not because the laws are absent, but because their interaction amplifies uncertainty beyond resolution. Sensitivity to initial conditions defines this regime. Differences too small to measure grow exponentially over time. Precision does not accumulate, it evaporates. No increase in computational power restores long-term predictability. This is where prediction loses meaning. Not because knowledge is insufficient, but because the system itself no longer supports convergence. The future becomes a space of possibilities, rather than a single trajectory. Beyond certain thresholds, precision becomes illusion. At these thresholds, constants no longer anchor behavior. They describe local structure, not global outcome. Models still operate, but their scope collapses. What was once a tool for prediction becomes a tool for classification after the fact. This is not a failure of mathematics or physics, it is the system revealing its own limits. Chaos is not disorder, it is determinism operating beyond the reach of simplification. When constants stop explaining, the question changes. It is no longer how precisely we can calculate, but how we understand systems whose behavior cannot be compressed into stable numbers. As systems grow in complexity, limits stop being obvious. In simple systems, cause and effect remain proportional. Small changes produce small responses. Prediction remains reliable. But complex systems do not behave this way. Complex systems are dominated by non-linearity. Effects are no longer proportional to causes. A minor perturbation can remain invisible for long periods, while a seemingly insignificant change can trigger large-scale transformation. In such systems, prediction becomes conditional, rather than absolute. Feedback loops amplify this behavior. Positive feedback reinforces change, while negative feedback resists it. For long periods, these forces can appear balanced. The system seems stable. But stability in complex systems is often deceptive. It is not the absence of change, but the containment of change within invisible thresholds. These thresholds define regions of stability. As long as a system operates within them, constants appear reliable, and models hold. But thresholds accumulate pressure silently. Stress does not announce itself. It integrates slowly, distributed across time and structure. This is why collapse often appears sudden. What looks like an abrupt failure is usually the result of long-term accumulation crossing a critical boundary. The transition is rapid, but the process is not. Climate systems illustrate this clearly. Temperature, circulation, and feedbacks interact across scales. Small, persistent changes accumulate until tipping points are reached. Once crossed, the system reorganizes faster than correction is possible. The same logic applies to turbulence. Smooth flow persists until energy input exceeds a critical limit. Beyond that threshold, order dissolves into chaotic motion, not gradually, but abruptly. Financial systems behave similarly. Long periods of apparent stability mask growing fragility. Leverage, feedback, and correlation accumulate until a threshold is crossed. Collapse then appears sudden, even though its causes were long in formation. In complex systems, limits are not lines, they are regions. And collapse is not a surprise. It is the moment when accumulated stress becomes structure-changing. Collapse is often treated as failure, as error, as breakdown. But in complex systems, collapse is not an accident. It is a phase transition. When a system reaches the limits of its form, it does not slowly degrade into nothing. It changes regime. The structure that once stabilized behavior exhausts its capacity to adapt. What collapses is not the system itself, but the form through which it was organized. Collapse marks the point where existing rules no longer apply, where constants lose their anchoring role, where optimization stops converging. At that moment, the system must either reorganize at another scale, or dissolve into simpler components. This process is not chaotic by default, it is structured. It follows internal constraints, accumulated feedbacks, and historical pathways. Collapse is the system expressing that its previous configuration is no longer viable. Societies follow this logic. Political, economic, and cultural structures remain stable as long as complexity stays within manageable thresholds. When those thresholds are exceeded, institutions do not fail randomly. They lose coherence. Forms that once coordinated collective behavior become sources of instability. Theories behave the same way. Conceptual frameworks remain powerful within certain domains. But when anomalies accumulate beyond accommodation, theories do not gradually improve. They fracture, reorganize, or are replaced. What collapses is explanatory form, not understanding itself. Civilizations, likewise, do not vanish overnight. They redistribute. They fragment. They transform into new cultural, ecological, and social configurations. Collapse is not disappearance. It is reconfiguration under constraint. Seen this way, collapse is not the opposite of structure. It is structure revealing its limits, a necessary transition when form can no longer sustain function.